Alright guys, this is 0654 Summer 19 paper 4.1 and we're looking at the physics questions obviously. Question number 3. Alright, this should be familiar to you guys from the mock. We were looking at calculating the current in a lamp I, and we're told what the value of that current is. Now I hope most people had no problem with this. Only thing I really want to highlight is a couple of things. Really, one, you've been given the answer already. So if you have no idea what to do here, then you need to think, okay, I've been given two numbers. How can I combine those two numbers to make the answer that they want me to give? Okay. Now, hopefully, most of you can see straight off is that that is simply a ratio question. If we take 12 and divide it by 30, we get 0.4. Okay. So if you're really not sure, then that's one way of doing this. Now, hopefully, what came to most of you guys' minds is the fact that we know that V is equal to I times R using our triangle method. Okay, that suggests then that I is the ratio of V to R, and therefore 12 divided by 30, 0.4. I really want to get you into the habit here of identifying variables. Okay, we're told R, we're told V. Think of a way, whatever way you want, to highlight those variables to yourself. Yeah. I like circling these things because I know that they're important. I can ignore the rest of this. As long as I know resistance and voltage here, I should be able to get the answer. Okay, we're then asked to calculate the power used by the lamp. Again, we've got another equation, P equal to I times V. Now again, you need to think of ways of remembering this yourself. For some reason, I think of Ver and PIV. It's just because that's the way that they work together in my mind. V equal to IR, P equal to IV, PIV. Okay, here's our P equal to I times V. We're told I in the question above, and we're told V in the question above. So there's quite a lot of referring back that you have to do in this question. I times V, 0.4 times 12 equal to 4.8. Now, a small point here, it's not required, okay? It's not required in your 0654, but I think it's really helpful to try, if you can, to remember these two equations I've highlighted here. P equal to I squared R and P equal to V squared over R. The reason being is that you never know when you're going to need these kind of equations, and you can also do some good checking. If you take your P equal to IV and you've calculated it and you want to do a bit of checking back, one way to check back is to try the other equation. If you take, for example, I square it and then multiply by R, you would hope that you're going to get the same answer. Okay, we could try that right now. Okay, I squared, we've got 0.4 squared, and then we've got 30 as our resistance. Okay, this 0.4 squared is, I think it's 0.16 times 30. 0.16 times 30, yeah, absolutely, 4.8 watts, okay? Just be aware that those two equations exist. You will never be asked explicitly to use them. They are equations which you might need. Okay, last one. Lots of calculations, which is nice here because hopefully we're getting into this recall. Q equal to IT. Okay, I think I mentioned this to a couple of you guys before. Quit. All right, QIT. If you don't know this equation, you should be quitting. I don't know, whatever way you can to think this up. Now, the key point here is that you are told a time in minutes. Yeah, anytime you see minutes, change those minutes into seconds. I've never seen an answer in 0654 which involves using minutes, okay? You're asked to calculate charge. Charge is just the product of I times the time, 0.4 times my time in seconds, time in seconds, and that gives us 720 coulombs. Okay, so that was question 3A. Now let me just move on to question 3B. Now, this is a question about our electromagnetic induction. Do not worry if you find this difficult. We're coming on to this. Okay, we've got a generator here. Now we've got a generator here, and a generator looks a lot like a motor. Okay, really the construction is very similar. You have a magnetic field there, and you've got a coil. The difference between a motor and a generator, well, there's a couple of things. One, a motor takes electrical energy and converts it into kinetic. Okay, we know that a motor spins around, yeah? Well, that's taking the electrical energy, maybe even chemical energy, becoming electrical, and then into kinetic. The generator does the opposite. You may have experienced this from, say, a bicycle dynamo. Okay, it takes the kinetic energy in a system and turns it into electrical. Okay, so that's one thing that they have a big difference. Another big difference that they have is down here. Okay, a motor at this point has something called a commutator, and that was the thing which splits, which reverses the direction of the current as it flows through the coil. A generator has something else. A generator has these two things which are called slip rings, and they allow my connections to be made, and they allow the production of an AC current. Okay, so that's another point here, is that a motor only works with DC. Yeah, you cannot work this with an AC system. A generator produces AC. There's no such thing as a DC generator. Okay, so simply put, these rings are R. Make sure you label them. This coil is C. You could point it anyway, but make sure you do this. Okay, these are marks which people miss because they just simply read the question too quickly. They think nothing really is to be done here. CIE never, ever, ever asks you to not to do anything in a question. Now there's the next question, number 3, which I've actually deliberately left because I want to show the plotting of this. Okay, absolutely, you need to show the direction of the magnetic field here with an arrow. All right, magnetic fields in this kind of situation, well, in any situation, go from north to south. Now obviously these north and south belong to two separate magnets. Okay, however, it's still possible for us to join them up, okay, with field lines. So our magnetic field is going from north to south. Okay, please make sure you draw it. It says one arrow, so draw one arrow. Now, last point here, this is a bit tricky. The output is alternating, and then we need to describe the difference between direct and alternating current. Okay, now the real difference is that is about direction. Okay, our direct current travels in one direction. Okay, however, alternating current changes its direction. You may have seen this number before, 50 hertz. Well, that's like a frequency. Okay, alternating current has a frequency, and actually it has a frequency of 50 hertz. That's 50 times per second. And what that current is doing is those electrons, instead of just simply moving around from A to B, they're changing their direction backwards and forwards, backwards and forwards, backwards and forwards, 50 times every second. So in alternating current, actually the electrons don't really go anywhere. They don't flow from positive to negative. They kind of vibrate on the spot, if you like. They move backwards and move forwards. Well, anytime they move backwards and forwards, that's a current. They give off energy, and that allows us to use, and we're able to use that through our components. All right, last one. This is a big question. Motorcycle is noisy. We're talking about sound waves. Okay, these C and R. C is a compression. That's where our particles are close together. Yeah. Rarefactions are where they're far apart. Okay. I like to think of the accordion. It's a musical instrument, pushing together and pulling apart. Yeah. My particles are moving together, compression, and pulling apart, a rarefaction. Now, in this question, we're asked what happens to the positions of these guys if the pitch of the sound increases. And this is a classic CIE trick to see if you understand what we mean by pitch and then apply it. Okay, the pitch of a sound, whether it's high or low, is to do with its frequency. Okay, if we have a high pitch, it has high frequency. Similarly, low pitch, low frequency. Okay, so really we're talking here about high frequency. The question here is about position. So really, if we want to think about position, we need to think about wavelength, remembering that from one compression to the next is one wavelength. Similarly, from one rarefaction to the next is also one wavelength. So we want to think about that position. Okay, and actually, as the frequency goes up, that wavelength goes down. Why? Well, let's just think about our equation which links these two things together. Let's go over here. V equal to F lambda. The speed of sound is constant. I'm going to put a dot there. Now what we're saying is that frequency is going up. Well, if we've got a constant number on the left, we're saying the frequency goes up, then the wavelength must go down. There's no other way of maintaining this constant number if the wavelength doesn't go down now. So frequency up, wavelength down. As a result, these things get closer together because higher frequency waves are produced, which means a shorter wavelength.